Unit 1, Lesson 5, Definition of the Derivative and Differentiability. First, let's recall the definition for the average rate of change. Now, an average rate of change is going to be the slope of the secant line. So what is a secant line? Well, let's take a look at this graph down here. Here's my curved function, f of x, and there are 2 points marked on here, a comma f of a, x comma f of x. And this line is the secant line. It's a line that passes through any 2 points on a function. So if the average rate of change is the slope of the secant line, then we need change in y over change in x. So if we look at the function notation down here, our y values are f of x and f of a, divided by the change in x, our x values are x and a. This is our average rate of change, basically just a slope. What about the instantaneous rate of change? This is the slope of the tangent line. A tangent line passes through a function at exactly 1 point. So if we come back over here to this graph and let's label the x values down here on the x-axis, I can't calculate the slope through 2 different points if I'm looking for a tangent line. A tangent line is going to pass through exactly 1 point. This is the example of a tangent line that passes through x equals a only. So we're going to pull this point to a. So the slope of a tangent line is a limit. It's the limit as x approaches a of our average rate of change formula, f of x minus f of a all over x minus a. Now this is the derivative of the function at a. This is the first definition of the derivative. When we're talking about an instantaneous rate of change, this is the derivative. Sometimes half of the battle is understanding what the question is asking for. The phrase instantaneous rate of change means find the derivative. Slope of the tangent line, that's the derivative. Derivative means derivative. So we have to know that all of these phrases are asking for the same thing. The problem with this definition of the derivative is that it only works when you're looking for the derivative at a specific x equals a. This is only going to give you the slope of the tangent line right here at a, and it's not going to give you the slope of any other tangent line. So that's why I have this graph here. Notice it looks identical except for how I labeled the points. Instead of thinking of this as 2 different x values, x and a, I've labeled this one as the first x value is x, and then the second one is just a little bit away from there. I've added h to x to move a little bit to the right. So this space in between the 2 of them is my h. So the logic stays the same, but the notation changes. Instead of thinking of this as the limit as x approaches a, I'm going to think of this as, let's think of the gap between the 2 getting smaller. Or in other words, the limit as h, the distance between them, goes to 0. And then what are we looking at? The slope. So the slope is the change in y, f of x plus h, minus f of x, all over the change in x. So that's x plus h minus x. Well, as it turns out, x minus x, those cancel out. So our definition of the derivative, the limit as h approaches 0 of f of x plus h minus f of x all over h, is the derivative. And what's nice is this will give you the derivative at any x. So you could plug in this x value to get the slope of the tangent line here, but I can plug in a different x value into the function and I will get the derivative or the slope of the tangent line at any x that I want. You have to have both of these limits memorized because you need to recognize both of them as the definition of the derivative. So if we're trying to say that a function has a derivative that exists, we say it's differentiable. If the derivative exists, it's differentiable. Now, we just went over that a derivative by definition is a limit. So in order for any limit to exist, it has to be two-sided, meaning the limit as x approaches a from the right of f of x minus f of a all over x minus a has to be equal to the limit as x approaches a from the left of f of x minus f of a all over x minus a. And if we just described the derivative as the slope, then we're talking about the slope of the tangent line, or the slope from the right side has to equal the slope from the left in order to say it's differentiable. The derivative is the slope of the tangent line, not just the y value. All right, I'm going to go a little bit out of order for this lesson. I want to jump to the back page, starting with multiple choice number 4. So take a second, turn to number 4. I want to just stick with this idea of the definition of the derivative, because you're not going to actually have to work out the definition of the derivative this year. I know Mr. Brown tortured you with that last year, and you had to work them all out with the limit definition before he showed you the shortcut rules. You already know the shortcut rules. You're not going to have to work out derivatives with the limit. However, you are going to have to recognize the definition as the derivative. Here's what I mean. Number 4 says, suppose the limit as x approaches 0, g of x minus g of 0 all over x equals 1. It follows necessarily that, and I've got a bunch of things that I have to decide from here. Well, the limit as x approaches 0 of g of x minus g of 0 all over x, it is missing in the bottom the very explicit change in x, but look at the values I have here, x and 0. X minus 0 is just x. This is, by definition, the definition of the derivative of g at 0. So it's necessarily true that g prime of 0 is 1. Okay, now that we've seen an example of how you're just supposed to recognize that as the definition of the derivative, let's go back. We've talked about how to decide a function is differentiable and what the definition of the derivative is. When is a function not differentiable? First, at any point of discontinuity. So any hole, any jump, any asymptote, if a function is not continuous, it's not differentiable. The second place where a function is not differentiable is at a corner or a cusp in the graph. Basically, this means that the right-hand derivative is not equal to the left-hand derivative. And like we said before, since we're talking about derivative, we mean slope. So right-hand derivative means the slope from the right is not equal to the slope from the left. Let's do an example of each. The example I'm going to use for corner is absolute value of x, because this is one that you should be able to recognize as kind of looks like a V, and its turning point is at the origin. So two different ways I want to explain this. If we're talking about the derivative as the slope coming in from the left side, the slope of this line is -1, so that's the slope from the left, and then the slope from the right side is +1. We could also see this algebraically because absolute value is a piecewise function. So we could rewrite this as it's -x as long as x is less than 0 and +x as long as x is greater than or equal to 0. So I promised you that you wouldn't have to evaluate a derivative by definition. So let's go over our derivative rules. If I wanted to take the derivative of this piecewise function, then the derivative of -x would just be its coefficient -1, as long as x is less than 0. And the derivative of x is just 1 for x greater than or equal to 0. And notice that those are corresponding to the slopes of the line. Why? Because the derivative is the slope of the tangent line. And if your function itself is linear, well, then the derivative is just the slope of the line. Therefore, the derivative at 0 doesn't exist because the right-hand derivative is not equal to the left-hand derivative. Two different slopes. It's good just to make mention that it's really only 0 that is the issue, because if I were to pick, I don't know, let's say x equals 2, well then the slope from the left and the right of 2 is both positive 1, because we're at the same part of the piecewise function. So it's only where the corner occurs that is not differentiable. But in terms of then its entire domain, if we're including the entire domain, then we would say the absolute value is not differentiable because the derivative at 0 does not exist. To give an example of a cusp, let's look at f of x equals x to the 2/3 power. And we're going to be looking again at x equals 0. So if you plug this into the graphing calculator, you're going to see that it's not two straight lines, but two curved lines that make a sharp turn at 0. That's really the only difference between a corner and a cusp. A cusp is created by curved lines, whereas a corner is formed by linear functions. So again, I'm not going to do the derivative as the limit, but I'm going to remind you of our power rule. Power rule says take the exponent, multiply it down to the front, and then subtract 1 from your existing exponent. So my derivative is going to be 2/3 x to the negative 1/3. Well, a negative exponent, that's going to shoot that x into the denominator. Oh no, if x is in the denominator, then it certainly can't be 0. 0 in the denominator is undefined. Therefore, f prime of 0 doesn't exist because f prime of x is undefined at x equals 0. Last issue that we could have is a point where the function has a vertical tangent line. A vertical tangent line. Well, the derivative is the slope of the tangent line. And vertical lines have no slope. So let's use the example f of x equals cube root of x. If you take a look at the graph in the calculator, you're going to see this S sort of shape where it curves this way and then switches to this way. So our vertical tangent line occurs here at x equals 0. The only line that can pass through this curve at exactly one point is vertical. Let's show this derivative again without having to do the definition. Cube root is the same as the 1/3 exponent. So now we can use our power rule to take the derivative. Multiply down the 1/3 and subtract 1 from the exponent. Oh, there's that negative exponent again. Negative exponent shoots this into the denominator. Now we have the same issue as we did before. X can't be 0 because it makes it undefined, so the derivative at 0 doesn't exist. Differentiability implies continuity. Differentiability implies continuity. This means if f of x is differentiable, then f of x must be continuous. All right, so we reviewed our power rule. On the next page, just formally reviews the power rule. You multiply down the exponent and then subtract 1. I also put in here derivative of a constant. The derivative of a constant is 0, so the derivative of 2 is 0, 3 is 0, and so on. There are a few functions that we need to have memorized, are trig functions. The derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared, otherwise 1 over cos squared. The derivative of cosecant is negative cosecant x, cotan x. The derivative of secant is secant times tangent. And the derivative of cotangent is negative cosecant squared x, or 1 over sine squared x. You need to just have these memorized, and unfortunately, you get no formula sheet the day of the AP exam. So you need to have them memorized. That's it. Start some flashcards. So let's move to some examples. Find a and b to make f of x differentiable. And you'll notice that f of x is a piecewise function. It's 2x plus a for all x less than or equal to 1, and b times x squared minus 1 for all x greater than 1. It's important to note that this is asking make f of x differentiable, not just continuous. So we would start by taking the derivative. The derivative of a piecewise function kind of sounds scary, but it's really not. You just take the derivative of the top, so the derivative of 2 times x, that's just 2, and then we've got this plus a, but a is going to be a constant, so that goes to 0, and it keeps its domain. Then you go to the bottom function and do the power rule. We're going to multiply the 2 down to the b, and then subtract 1 from the exponent, so 2bx to the first, or 2bx, and then the minus 1, that goes to 0, keep the domain. So now that we have the derivative from the left should be equal to the derivative from the right, where this is split at x equals 1. So let's plug in 1 for x and set it equal, that these two derivatives from the left and the right would have to be equal when x is equal to 1. This is a nice simple equation to solve for b. Now this is great that we now know b equals 1, but what about a? Now a dropped out when we took the derivative, so we have to remember for a function to be differentiable, then it must be continuous. So let's go back to our original function and plug in that we now know b is 1. So I'm basically upgrading this expression, bx squared minus 1, knowing that b is 1, that's just 1x squared minus 1, or x squared minus 1. Now if the function is continuous, then these y values have to match from the left and from the right. The derivative is about the slopes matching, continuous is about them meeting at the same y value. So let's plug in x equals 1 and set these two equal. So when x is 1, both y values have to be the same. So we have this nice easy equation. 1 squared is 1, minus 1 is 0. So a would have to be negative 2. The question asked for both a and b. Now, what's going to make these more difficult is when we look at something like number 2, it's the algebra that's going to be increased on you in terms of the level of difficulty. This is the concept. So if a function is differentiable, it must be continuous. I knew I was going to need some more space, so I copied this page again so that we can do number 2 and have enough room. So again, we want differentiable, so we're going to start by taking the derivative. So power rule on the top, multiply down the 4, and subtract 1 from the exponent. The derivative of 5x is just 5, and you keep the domain. Power rule on the bottom, multiply down the 2, subtract 1 from the exponent, so 2bx, and then the derivative of 3x is 3. Again, keep the domain. Now, where this is split, at x equals 2, we can plug in the x as 2 and say that these slopes or these derivatives have to be equal. So plugging 2 into the top expression, 4a times 2 cubed plus 5 equals 2b times 2, plugging in 2 for x, minus 3. Let's simplify. And I still have two variables. There's an a and a b. So I'm not going to be able to solve just for one. But what we can do is isolate one of the variables. It really doesn't matter which way you're going to go, but I kind of notice that if I isolate b, I'm going to be dividing away the 4, and that's going to give me a whole number, where if I go the other way around and divide by 32, I get a fraction. So let's avoid the fraction and solve for b. So first I added over the 3. Now let's divide everybody by 4. And I haven't solved for b yet, but at least I have an expression for b. So remember, we're looking at this here. Let's go back to the idea that if it's differentiable, it must be continuous. And let's plug in 2 for x into the original equation. Everywhere there is an x, I put a 2. Let's simplify. And again, we get an expression in terms of a and b. So since down here I decide to solve for b, let's solve for b on this one as well. So add over the 6 and divide by 4. And now I've got an expression for b again. Now remember, this is the same a and b throughout the problem. So if b is equal to 8a plus 2 and also equal to 4a plus 4, we could set them equal to each other. That's just substitution. If they're both equal to b, they're equal to each other. Let's solve for a. Subtract over that 2 and divide by 4. We have a should be 1/2 or 0.5. But we're not quite done because we got to find a and b. But I've got two different expressions for b here. Pick your favorite one, and we can find b just by plugging in that a is 1/2. So therefore b is equal to 6. Now, there was more than one way to solve this problem. There's no problem with isolating a. You could even show off your fancy algebra skills and have left it in this expression and solve this as a system of equation, either by elimination, or I chose to do substitution. But your algebra skills are whatever you decide to do to solve a problem like this, but this is what BC Calculus does. It takes a concept that you learned in pre-calc, like example 1, and it just kind of one-ups it. It makes you remember your algebra. It makes you recall skills that you haven't used maybe as much. It pulls it all together. All right, let's go through our remaining multiple choice. Gives us this piecewise function for f of x, and we have to decide which one of these is true. So first one says f of x is not continuous at x equals 1. Well, remember, continuity is the y values. So if I plug in 1 to the top expression and then 1 to the bottom expression, both of them give me the solution of 1. So yes, it is continuous. B says it is continuous at 1, but the derivative doesn't exist. Well, we have to take the derivative to see if it exists. So power rule on the top, multiply down that 2, keeping our domain. And derivative of the bottom is just the constant 2. Remember that 1 goes to 0, again keeping its domain. So this means when I plug in 1 for x, I get 2 on the top part of the piecewise function, and it is the constant 2 on the bottom part of the function, so the derivative does exist. So B is out because it says that it does not exist. C says f prime at 1 exists and is equal to 1. Well, it exists, but the derivative is not 1, it's 2. Well, that's exactly what part B is saying. F prime at 1 equals 2. And the reason why E is true is because if the function is continuous, then the limit exists. Notice that from the left and from the right, the y values meet or are both equal to 1. We already did number 4, so let's jump to 5. 5, 6, 7, and 8 are all the same type of question. In pre-calc, you had to work out the derivative by its definition, and it's for you to understand where it's coming from. It's a limit as that secant line becomes the tangent line. However, I don't want you to use that definition of the derivative anymore. I want you to recognize, hey, isn't this the derivative? And then use your shortcut rules. Let me show you what I mean. Take a look at number 5. The limit as h goes to 0. Right there, that is your red flag. The limit as h goes to 0. When you see that h, I want you to be thinking derivative. X plus h cubed minus x cubed all over 8 at x equals 2. The definition of the derivative is the limit as h goes to 0 of any f of x plus h minus f of x all over h. So this whole expression is really asking you for the derivative. But of what? What's the function f of x? Well, match it up. X plus h cubed minus x cubed. F of x plus h minus f of x. Well, f of x is x cubed. So I don't have to do this as a limit. I know a shortcut rule, and I want you to use the shortcut rules. Multiply down the 3, subtract 1 from the exponent. The derivative is 3x squared. Well, they want it at x equals 2, so great, let's plug in 2. So 3 times 2 squared is 12. Choice B. Let's look at number 6. again, the limit as h goes to 0 of sine pi over 2 plus h minus 1 all over h. This limit as h goes to 0, that's got to trigger, hey, definition of the derivative. So what's different this time? Well, f of x plus h minus f of x isn't in terms of x here. We've got some numbers. Sine of pi over 2h. They've already plugged in where the x is pi over 2. So then where did this 1 come from? Well, it's supposed to be f of x. So if we put a pi over 2 in place of x, the sine of pi over 2 is 1. Remember, it's the same function, f of x plus h minus f of x. So if it's sine of pi over 2 plus h, then this must be representing sine of pi over 2, which is 1. Makes sense. So what is this question then really asking me? Because I don't want to do this as a limit. It's asking us for the derivative at pi over 2 if the function f of x is sine x. Well, wait a minute. We know a different way. Instead of the limit definition, the derivative of sine x is cos x. I told you have to memorize that. So plug in pi over 2, and our answer is 0. Choice C. Once you get the hang of these, they're so easy to spot. Number 7, the limit as h goes to 0. Uh-oh, definition of the derivative. We've got 2x plus h to the 5th minus 5x plus h cubed minus 2x to the 5th plus 5x cubed. Notice the first part of this and the second part of this are similar because it's the function at x plus h minus the function at x. Now this one's got a little bit of a snag because the minus sign distributes over this binomial, or if you have a polynomial with more than one term. So this part here is the f of x plus h, but this is f of x with the signs distributed. So f of x is 2x to the 5th minus 5x cubed. The one with the x plus h in it is a little bit truer to the signs because really what happens down here is if we were to factor out that -1, then that's where we see the actual signs of f of x. Long story short, I don't want to do the limit. I want to say I've got a power rule. Power rule says multiply down the exponent, then subtract 1. Multiply down, subtract 1. Carefully look for your answer. Here it is, choice D. All right, last one. Limit as h goes to 0. Definition of the derivative. F of x plus h minus f of x all over h. Well, this time they don't have an x in there. They've got the value 1/2. So this is the formal way of asking for the derivative evaluated at 1/2. Of what function, though? Well, f of x is going to have to be 5x squared. 5x to the 4th. Again, I don't want to do this as the limit. I want to take advantage of my power rule, multiply down the 4, subtract 1 from the exponent, and now we just have to plug in 1/2 since it didn't ask us to evaluate it at x. Remember, you're going to have to do a lot of practice without the use of the calculator. So 1/2 cubed is 1/8. So my answer is 20/8. Or if I had to reduce, this one isn't multiple choice, we could reduce to 5/2. Remember though, when it's free response, you can leave the answer. I could have even left it like this, and I don't have to simplify. Great job, and I'll see you in the next lesson.